The morning of February 19th, 1945, a makeshift laboratory in the Kure Naval Arsenal, 20 miles south of Hiroshima, Commander Tanaka Yoshio of the Imperial Japanese Navy's Technical Research Division stood over a workbench, staring at an object that should not exist. In his hands was an American 5-inch artillery shell, recovered intact from the waters off Iwo Jima 3 days earlier. The shell had failed to detonate when it struck the ocean surface during the pre-invasion bombardment, a statistical anomaly that occurred perhaps once in every 10,000 rounds. But it was not the shell itself that commanded Tanaka's attention. It was the device screwed into its nose. The fuse assembly, designated VT by American nomenclature, contained what appeared to be a complete miniature radio transmitter. Through the transparent potting compound that protected the internal components, Tanaka could see vacuum tubes no larger than his thumb, capacitors, resistors, and circuitry so intricate it seemed designed for a tabletop radio set, not a projectile meant to be fired at 20,000 times the force of gravity. He had spent the previous evening carefully removing the fuse from the shell body, a process that required 3 hours and absolute concentration, because one mistake would trigger the detonator and obliterate both the evidence and himself. Now, examining the disassembled components under laboratory lighting, Tanaka faced a realization that would fundamentally alter Japanese understanding of what they were facing in this war. The Americans had not only solved a problem that Japanese engineers had declared theoretically impossible, they had solved it so completely that they were manufacturing these devices by the tens of thousands, loading them into artillery shells, and firing them as casually as conventional ammunition. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Tanaka's hands trembled slightly as he made notes in his laboratory journal. Not from fear, but from the weight of understanding what this small device represented. Japan had been fighting this war under assumptions about American industrial capacity that were catastrophically wrong. This single fuse, no larger than a wine bottle, contained more advanced electronics than existed in most Japanese university research laboratories, and the Americans were firing them by the thousands every day, treating them as expendable munitions. The story of how Japanese engineers came to understand and fear the proximity fuse began not in February 1945, but 3 years earlier, in the laboratories of Tokyo Imperial University and the naval research facilities at Yokosuka, where Japanese scientists had pursued the same theoretical goal and reached the same conclusion as their German counterparts. It was impossible. The Imperial Japanese Navy's interest in proximity fuses dated to 1938, when increasing tensions with the United States prompted urgent reviews of anti-aircraft capabilities. Japanese naval doctrine anticipated fighting American carrier forces in decisive surface engagements. American aircraft would be the primary threat. Yet Japanese anti-aircraft effectiveness was abysmal. During combat trials in 1939, it required an average of 1,600 rounds of Type 96 25mm ammunition to down a single target sleeve towed at modest speed and altitude. Against actual combat aircraft performing evasive maneuvers, the hit rate would be far worse. The fundamental problem was identical to what every major power faced. Anti-aircraft guns relied on either direct hits, which required extraordinary accuracy against fast-moving targets, or timed fuses set to explode at predetermined altitudes. In practice, timed fuses were notoriously unreliable. Shell trajectories varied, with temperature, humidity, and barrel wear. Target altitudes were difficult to estimate accurately. By the time a shell reached its preset detonation point, the target aircraft had usually moved elsewhere. The solution, in theory, was obvious. Create a fuse that could detect its own proximity to a target and detonate automatically. Simple in concept. But Japanese researchers quickly discovered the engineering challenges were overwhelming. Professor Hidetsugu Yagi of Tohoku Imperial University, whose research on directional antennas had pioneered radio engineering in Japan during the 1920s, was consulted in 1939 about the feasibility of a radio-based proximity detector. Yagi, whose antenna designs would ironically be used extensively by Allied forces during the war, conducted preliminary analysis and concluded the concept was theoretically sound. A miniature radio transmitter could emit signals that would reflect off an approaching aircraft. Doppler, frequency shift in the reflected signal, could trigger detonation at optimal range. But Yagi identified what he termed insurmountable practical obstacles. First, the radio components would need to be miniaturized to fit inside an artillery shell nose, leaving room for the explosive charge. Vacuum tubes of the era were fragile glass bulbs filled with delicate internal structures. The smallest tubes available in Japan, manufactured for hearing aids and portable radios, were approximately 2 inches long and far too fragile for military applications. Second, and more critically, the entire assembly would need to survive being fired from a gun. When a 5-inch naval gun fired, the shell accelerated from rest to over 2,000 feet per second in less than 20 feet of barrel length. The acceleration forces were approximately 20,000 times Earth's gravity. Every component would experience crushing forces equivalent to being struck by a sledgehammer while simultaneously being spun at 25,000 revolutions per minute as the shell engaged the rifling. Yagi calculated that conventional vacuum tubes would shatter instantly under such forces. The glass envelopes would fracture, the filaments would snap, and the delicate grid structures would collapse. Even if, by some miracle, the tubes survived being fired, they would then need to function perfectly during the few seconds of flight time. The electronics would need to generate radio signals, receive and process reflections, discriminate between valid targets and ground clutter, and trigger the detonator at precisely the right moment. All of this, while spinning violently and experiencing extreme temperature variations from the heat of firing to the frigid air at altitude. The Technical Research Division of the Imperial Japanese Navy, headquartered at Yokosuka Naval Arsenal, pursued proximity fuse development from 1939 through 1942. Multiple approaches were tested. Acoustic fuses that would trigger on aircraft engine noise proved unreliable. Wind noise and the shell's own supersonic passage created overwhelming acoustic interference. Propeller sounds were difficult to distinguish from background noise at combat ranges. Electrostatic fuses designed to detect the electrical charge on aircraft surfaces worked inconsistently. The detection range was too short, often less than 10 meters, which provided insufficient time for the detonation sequence to complete before the shell passed the target. Photoelectric fuses using light sensors showed promise in laboratory conditions, but failed utterly in field testing. Clouds, smoke, and haze blocked the sensors. Bright sunlight caused false triggers. The sensors were so sensitive to shock that they rarely survived being fired. By mid-1942, after investing substantial resources and testing over 40 different design concepts, Japanese researchers reached the same conclusion as their German colleagues. Proximity fuses, while theoretically possible, could not be made practical with available technology. The miniaturization requirements exceeded Japanese manufacturing capabilities. The ruggedness requirements exceeded material science limitations. And even if these obstacles could be overcome, the cost would be prohibitive. Japan's industrial base was already strained, supporting naval construction, aircraft production, and basic ammunition manufacturing. Diverting resources to develop expensive, complex fuses for anti-aircraft shells seemed wasteful when those resources could produce more ships, planes, and conventional ammunition. Captain Nakajima Tadashi, who directed the Navy's proximity fuse research program until its cancellation in October 1942, wrote in his final report that the program had been valuable despite its failure. The research had definitively established the limits of what was technically feasible. American and British scientists, Nakajima reasoned, would reach identical conclusions when they pursued similar research. Proximity fuses would remain theoretical curiosities, interesting physics problems that could not be translated into practical weapons. This assessment was filed, archived, and largely forgotten as Japan turned its attention to more immediate concerns. The war was going badly. Guadalcanal had become a meat grinder, consuming men and ships faster than they could be replaced. Industrial production was falling short of targets. American submarines were strangling supply lines. In this context, abandoning research on impossible weapons seemed like prudent resource allocation. Nakajima's conclusion that American scientists would fail where Japanese researchers had failed was the kind of assumption that seemed reasonable in 1942. It was also catastrophically wrong. The first indication that something had changed came in January 1943, though Japanese intelligence analysts did not recognize its significance at the time. Radio intercepts from American naval forces in the Solomon Islands included references to VT ammunition and unusual success rates in anti-aircraft engagements. On January 5th, the heavy cruiser USS Helena had engaged Japanese aircraft attacking near Guadalcanal. Post-action reports, partially decoded by Japanese naval intelligence, indicated Helena had downed an enemy aircraft with only 3 salvos from its 5-inch battery. This seemed statistically improbable, but not impossible. Perhaps the American gunners had been exceptionally skilled or extraordinarily lucky. Over the following months, similar reports accumulated. American ships were consistently achieving anti-aircraft kill rates that seemed too high. Japanese pilots returning from attacks on American naval forces reported shells exploding near their aircraft without direct impacts, creating shrapnel patterns in mid-air. This was not unheard of. Timed fuses occasionally functioned as intended, but the frequency seemed unusual. By mid-1943, Japanese naval intelligence had compiled enough intercepts and pilot reports to warrant investigation. A special analysis team was formed to determine whether American anti-aircraft effectiveness had genuinely improved or whether Japanese forces were simply encountering better-trained gunners and modern fire control systems. The conclusion, filed in August 1943, was that American gunnery had indeed improved, probably due to better radar-directed fire control and more extensive crew training. There was no indication of any revolutionary new technology. This assessment would prove to be one of the most consequential intelligence failures of the Pacific War. The truth was being fired at Japanese forces every day, but the evidence kept sinking into the ocean. Proximity-fused shells that detonated properly left no physical evidence to examine. Dud shells, which might have revealed the secret, always sank when they hit water. The few that remained on the surface were usually destroyed by the explosive charges within when seawater eventually corroded through the casing. American security protocols strictly forbade use of proximity fuses over land where dud shells might be recovered. In the Pacific theater, where most combat occurred over open ocean, this restriction was relatively easy to maintain. Proximity fuses were used freely in naval anti-aircraft batteries because any duds would sink beyond Japanese reach. The security worked perfectly until it did not. November 1944. The Philippines Campaign. As American forces advanced toward Manila, naval gunfire support missions increased dramatically. American destroyers and cruisers positioned offshore provided artillery support for ground forces, firing thousands of shells daily. Most were conventional high-explosive rounds with standard impact fuses, but some were proximity-fused shells used when air attacks threatened the fleet. The restrictions on land use had been quietly relaxed. Combat necessity trumped security concerns. On November 18th, during fighting near Ormoc Bay, a Japanese patrol discovered an unexploded American 5-inch shell partially buried in soft mud along the shoreline. The shell had apparently been fired at low angle, struck the mud at an oblique trajectory that absorbed the impact without triggering the fuse, and remained intact. The patrol, following standard procedures for handling unexploded ordnance, marked the location and reported to the local army headquarters. Explosive ordnance disposal teams from the Imperial Japanese Army arrived within hours. They were accustomed to dealing with American bombs and shells. Unexploded munitions were hazardous but valuable. The steel casings could be melted down for scrap, and sometimes the explosive fill could be recovered for use in Japanese munitions. This shell was different. The disposal team sergeant immediately noticed the unusual fuse assembly. Instead of the standard threaded impact fuse, this shell had a larger, more complex device, with what appeared to be a transparent or translucent nose section. Visible inside were components that looked nothing like conventional fuse mechanisms. The sergeant made the correct decision. This required expert analysis. The shell was carefully transported to Manila, where Imperial Japanese Army Technical Intelligence maintained a small laboratory. There, on November 22, 1944, Japanese engineers got their first look at an intact American proximity fuse. The initial examination was conducted with appropriate caution. Nobody knew if this was a booby trap. Some American munitions had been discovered with anti-handling devices designed to detonate if disturbed, but careful X-ray imaging, using one of the few portable X-ray units available in the Philippines, revealed no obvious anti-tampering mechanisms. What it did reveal was astonishing. The fuse assembly contained what appeared to be electronic components, vacuum tubes, capacitors, resistors, all miniaturized to an extraordinary degree and packed into a space no larger than a man's fist. The engineers examining the X-rays initially assumed they were misinterpreting the images. This had to be something else. Perhaps a mechanical time delay mechanism with unusually shaped components. Perhaps an optical system with lenses that appeared electronic in X-rays. The idea that this could actually be a radio transmitter was not even considered, because everyone involved knew that radio transmitters could not survive being fired from a gun. The mystery was resolved 2 days later when the fuse was successfully disarmed and carefully disassembled. The components were exactly what they appeared to be. Vacuum tubes, genuine miniature vacuum tubes with glass envelopes, internal filaments, and grid structures. A transmitter circuit with inductors, capacitors, and resistors. A battery system using some kind of reserve electrolyte design. A detonator assembly with safety mechanisms. And all of it engineered to fit inside the nose of a standard 5-inch artillery shell. The engineer who performed the disassembly, whose name was recorded in the report as Lieutenant Yamamoto Kenji, made detailed drawings and took extensive notes. His report, forwarded to Tokyo on November 28 via courier, included a section titled Implications that demonstrated Yamamoto understood exactly what he was looking at. The Americans, Yamamoto wrote, had solved the proximity fuse problem. They had developed miniature vacuum tubes capable of surviving artillery acceleration. They had designed circuitry compact enough to fit in a shell nose while leaving room for an adequate explosive charge. They had created a battery system that could provide power on demand. And most significantly, they were using these devices as expendable munitions, which implied they could manufacture them in large quantities at acceptable cost. Yamamoto's report concluded with an assessment that must have been difficult to write. If this technology represented standard American ammunition rather than an experimental prototype, then Japanese anti-aircraft capabilities were obsolete. Worse, if Americans could miniaturize radio transmitters to this degree, what else had they miniaturized? What other technologies had they developed that Japanese intelligence knew nothing about? The report reached Tokyo in early December 1944 and triggered immediate action. The proximity fuse, the intact one from the Philippines, was ordered transported to Japan for detailed analysis. Several senior engineers from the Technical Research Division, including men who had worked on Japan's failed proximity fuse program in 1940 and 1941, were tasked with conducting comprehensive evaluation. Getting the fuse from Manila to Japan proved challenging. American submarines controlled the sea lanes. American aircraft dominated the skies. The fuse, packed in protective cushioning and sealed in a waterproof container, was loaded aboard a fast destroyer, making a supply run to Japan. The destroyer left Manila on December 15th and reached Kure Naval Arsenal on December 22nd after evading 2 submarine contacts and 1 aircraft patrol. The fuse arrived intact. On December 26, 1944, a team of 5 engineers began detailed examinations in a secured laboratory at Kure. Commander Tanaka Yoshio, who had worked on photoelectric fuse designs in 1941, led the team. What they discovered over the following weeks was both fascinating and profoundly disturbing. The vacuum tubes were engineering marvels. Each tube was approximately 1 inch long and half an inch in diameter, far smaller than any tube manufactured in Japan. The glass envelopes were unusually thick and appeared to have been specially annealed to increase shock resistance. The internal elements, the filaments, grids, and plates, were constructed with heavier cross-sections than standard tubes. obviously designed to withstand acceleration forces. Testing revealed the tubes were remarkably robust. When subjected to shock loads that would instantly destroy conventional tubes, the proximity fuse tubes survived. They had been deliberately over-engineered for survival in what was, by any measure, the harshest environment imaginable for delicate electronics. The transmitter circuit was equally impressive. The designers had used printed circuit techniques, creating conductive paths on flat insulating boards rather than using conventional point-to-point wiring. This saved space, reduced weight, and improved reliability by eliminating solder joints that might fail under shock. The circuit design itself was elegant. The transmitter operated at approximately 180 MHz, a frequency high enough to provide good reflection, characteristics from aircraft, but low enough to be generated by miniature tubes. The receiver circuit used the same tubes in a different configuration, converting the transmitted signal and comparing it to the reflected return. When the Doppler shift reached a preset threshold, indicating the target was within lethal range, the circuit closed and sent a pulse to the detonator. The battery system used what Tanaka identified as a reserve electrolyte design. The battery plates and electrolyte were kept separate until activation. When the shell was fired, centrifugal force from the spinning projectile drove the liquid electrolyte into contact with the plates, generating electrical current. This meant the battery had effectively unlimited shelf life because there was no electrolyte contact to cause deterioration during storage. The detonator assembly included multiple safety mechanisms. The fuse could not arm until the shell had traveled a minimum distance from the gun, preventing premature detonation that might damage the firing ship. Wave suppression circuitry prevented premature triggering when shells were fired at low angles over water, where reflections from the sea surface might otherwise cause false detonations. And fail-safe mechanisms ensured that if the proximity detection system malfunctioned, the shell would still detonate on impact through a backup contact fuse. Every aspect of the design revealed careful thought about the practical requirements of a combat weapon. This was not a laboratory prototype or an experimental system. This was a mature, production-engineered device, designed to be manufactured in large quantities and to function reliably under combat conditions. Tanaka's team spent January and early February 1945 conducting tests, making measurements, and compiling data. They carefully powered the fuse using external batteries, confirming that the transmitter functioned and produced a detectable radio signal. They tested the battery's receiver sensitivity and measured its frequency response. They examined every component under microscopes, making detailed drawings and taking photographs. By mid-February, they had compiled a technical report that ran to over 100 pages of text, diagrams, and analysis. The report was comprehensive, but its conclusions could be summarized briefly. The American proximity fuse represented a technological achievement that exceeded Japanese capabilities by a margin so large that attempting to replicate it would be futile. But there was still a question that needed answering, and it was this question that led to the scene in Tanaka's laboratory on the morning of February 19th. The vacuum tubes, these miniature marvels of glass and metal, had supposedly survived being fired from a gun at 20,000 times the force of gravity. Tanaka and his team had examined the tubes carefully. They showed no obvious damage, no cracked envelopes, no broken filaments, but appearances could be deceiving. The only way to know for certain if these tubes could survive artillery firing was to test them. Tanaka had convinced his superiors to allocate resources for one firing test. A Japanese Type 89 12.7 cm naval gun, roughly equivalent to the American 5-inch guns, was prepared at the Kure testing range. The proximity fuse tubes, carefully removed from the American fuse assembly, were installed in a specially machined test fixture designed to hold them securely while recording acceleration forces. The test fixture was loaded into a shell casing. On February 19th, at 0800 hours, the gun was fired. The shell arced over the test range and impacted in a designated recovery area where the soft sand would cushion the landing. Recovery teams retrieved the shell within minutes. Tanaka personally supervised the extraction of the test fixture. His hands were shaking as he opened it, not from cold, the morning was relatively mild, but from anticipation and something close to dread. He knew what he was going to find, but part of him still hoped to be wrong. The vacuum tubes were intact. Not just intact, but functional. When connected to a test circuit back in the laboratory, they operated normally, generating and amplifying signals exactly as they had before being fired. These delicate glass devices, which Japanese engineers had concluded could not possibly survive artillery acceleration, had just survived being fired from a Japanese gun and were working perfectly. Tanaka sat down heavily on a laboratory stool, staring at the glowing filaments inside the tubes. Around him, the other engineers were silent, each processing the implications in his own way. This was the moment when everything changed, not the moment when they discovered the proximity fuse existed, not the moment when they realized Americans had solved the miniaturization problem. This was the moment when they understood, viscerally and undeniably, that they had been fighting a war based on completely false assumptions about what was possible. If Americans could make vacuum tubes that survived artillery firing, what else could they make? What other supposedly impossible problems had they solved while Japanese engineers had concluded those problems were unsolvable? The implications cascaded outward like ripples from a stone dropped in still water. The proximity fuse was not an isolated achievement. It represented a comprehensive superiority in materials science, manufacturing technology, quality control, and industrial organization. Consider what was required to produce such a device. The vacuum tubes needed special glass formulations that could withstand shock. That implied advanced glass manufacturing and materials research. The tubes needed to be manufactured to extremely tight tolerances. That implied precision manufacturing equipment and skilled workers. The tubes needed to be tested and quality controlled. That implied testing, systems, and statistical process controls. And all of this needed to happen at scale, because Americans were clearly using these fuses as standard ammunition. One proximity fuse was an impressive laboratory achievement. 10,000 proximity fuses represented an industrial infrastructure that Japan simply did not possess. Tanaka's final report, submitted to the Technical Research Division on February 28, 1945, was both a technical document and a strategic assessment. The technical sections described the fuse in exhaustive detail, providing specifications, circuit diagrams, and test results. But the report's conclusion was strategic, and it was damning. Japan had been fighting under the assumption that American industrial superiority was primarily quantitative. Americans could build more ships, more planes, more tanks, simply because they had larger factories and more workers. But the proximity fuse revealed that American superiority was also qualitative. Americans could build things that Japan could not build at all. The proximity fuse required vacuum tubes that could survive 20,000 gravities of acceleration. Japan could not manufacture such tubes. Even if Japanese engineers developed the necessary techniques, which would take years, Japan lacked the industrial infrastructure to produce them in meaningful quantities. The fuse required miniature circuit components manufactured to precision tolerances. Japan's electronics industry was already operating at maximum capacity, producing radios, radar sets, and radio equipment for aircraft. Diverting capacity to proximity fuses would mean reduced production of other critical equipment. The fuse required sophisticated battery systems, quality control processes, and testing procedures. Each of these represented capabilities that Japan either lacked entirely or possessed only in limited degree. But the most significant implication was psychological. Japanese military planning had been based on assumptions about American character and American capabilities. Americans, according to Japanese strategic thinking, were wealthy but soft, industrious but uncreative, capable of mass production but inferior in innovation and technical sophistication. The proximity fuse demolished those assumptions. This was not crude mass production. This was elegant engineering combined with manufacturing sophistication. This was innovation at the highest level, and Americans were producing these sophisticated devices in such quantities that they could afford to fire them as casually as conventional ammunition, knowing that most would detonate over water and sink, wasting all that embedded technology and manufacturing effort. That casual waste of expensive, sophisticated equipment demonstrated confidence that came from apparently unlimited productive capacity. By March 1945, additional proximity fuses had been recovered. One came from Iwo Jima, another from Okinawa, a third from a downed American aircraft near Kyushu. Each was examined, adding to the database of technical intelligence. The fuses showed minor variations, suggesting multiple manufacturers, but the core design was consistent. This was standardized, mass-produced equipment, not experimental prototypes. Japanese engineers noted small improvements in later fuses, refinements in circuit design and component layout that indicated ongoing development. Americans were not just manufacturing proximity fuses, they were continuing to improve them while manufacturing them, suggesting a degree of industrial agility that seemed almost incomprehensible. Reports from the field added operational context to the technical intelligence. Japanese pilots operating from bases in Kyushu and Shikoku reported that American naval vessels were becoming increasingly dangerous to attack. Anti-aircraft fire from American ships seemed to explode with impossible precision. Shells detonated near aircraft without direct hits, creating shrapnel clouds that were extremely difficult to evade. Kamikaze pilots, who accepted death as inevitable, reported that proximity-fused anti-aircraft fire made even approaching American ships problematic. The psychology of kamikaze operations depended on the pilot maintaining control until the final moment of impact. But proximity fuses detonated before impact, destroying aircraft while they were still maneuvering toward targets. Success rates for kamikaze attacks had been dropping steadily since late 1944. Japanese naval intelligence had attributed this to improved American fighter coverage and better ship handling. But now, with knowledge of proximity fuses, the statistics made terrible sense. American ships had become significantly harder to hit because their anti-aircraft defenses had become vastly more lethal. Intelligence estimates, compiled in March 1945, suggested that proximity fuses had reduced kamikaze effectiveness by approximately 40% compared to early 1944, when the tactic had first been employed. The actual figure was probably higher, but intelligence officers had no way of knowing how many kamikaze aircraft had been destroyed by proximity-fused shells versus conventional anti-aircraft fire. What they did know was that the tactic that had been Japan's best hope for inflicting significant losses on the American fleet was becoming progressively less effective. By April 1945, the strategic situation had deteriorated to the point where technical intelligence about proximity fuses seemed almost irrelevant. American forces had taken Iwo Jima and were assaulting Okinawa. American B-29 bombers were firebombing Japanese cities. The home islands were under blockade. Fuel shortages had grounded most of the remaining aircraft. Food shortages were becoming critical. In this context, learning that Americans possessed superior fuse technology was simply one more confirmation of a reality everyone already understood. Japan was losing the war. But for the engineers who had worked on proximity fuse analysis, the knowledge had a personal dimension that transcended strategic concerns. They had devoted years to solving problems they had concluded were impossible. Now they knew those problems were not impossible. They had simply been impossible for Japan, with available resources and technology. Tanaka, in a personal letter to Professor Yagi written in April 1945 but not sent until after the war, reflected on this realization. "We were not wrong in our analysis," Tanaka wrote. "The problems we identified were real. Miniaturizing vacuum tubes to survive artillery firing was extraordinarily difficult, but we concluded it was impossible because we could not imagine how to solve it with available technology. Americans solved it by developing new technology. They created new glass formulations, new tube designs, new manufacturing techniques. They did not accept the constraints we accepted. They changed the constraints. This represented a fundamental difference in approach. Japanese engineering culture emphasized working within limitations, optimizing existing technologies, and making incremental improvements. These were valuable approaches that had served Japan well in many contexts. But American engineering culture apparently emphasized removing limitations, developing new technologies, and accepting high risks in pursuit of breakthrough achievements. When faced with vacuum tubes that could not survive artillery firing, Japanese engineers had concluded proximity fuses were impractical. American engineers had apparently decided to invent new kinds of vacuum tubes. The proximity fuse was, in this sense, a perfect metaphor for why Japan was losing the war. Japanese military planning had been based on optimizing within constraints, the constraints of limited resources, limited industrial capacity, and limited technological infrastructure. American military planning had been based on removing constraints through massive application of resources, comprehensive industrial mobilization, and technological innovation on a scale that seemed almost reckless. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The end came in August 1945, not from proximity fuses, but from atomic weapons, another American technological achievement that Japanese scientists had considered theoretically possible but practically impossible given the resource requirements. The proximity fuse and the atomic bomb represented different points on the same spectrum. Both required solving problems that seemed insurmountable. Both required massive resource investments. Both demonstrated American willingness to pursue difficult technical goals, despite enormous costs and uncertain outcomes. In the aftermath of the war, as Japan began the long process of reconstruction, some of the engineers who had analyzed American proximity fuses found themselves working on rebuilding Japanese industry. They brought with them knowledge of American manufacturing techniques, quality control processes, and approaches to technical problem-solving. Tanaka, who survived the war and worked in the post-war electronics industry, later reflected that the proximity fuse had taught him more about American industrial culture than any number of intelligence reports or captured documents could have conveyed. It taught him that Americans approached technical problems with a fundamental optimism that solutions existed if enough resources and effort were applied. It taught him that American industry valued innovation and continuous improvement, even during mass production. It taught him that American quality control processes assumed defects could be eliminated through systematic analysis rather than accepted as inevitable. These lessons, learned from a device designed to kill Japanese forces, became part of the foundation for Japan's post-war industrial recovery. The irony was not lost on those who remembered the wartime proximity fuse analysis. One of the vacuum tubes from the original proximity fuse, the one recovered from the Philippines in November 1944, was preserved after the war. It eventually made its way to the museum at the Technical Research and Development Institute of the Japan Ministry of Defense, where it remains today. The tube, slightly smaller than a man's thumb, sits in a display case alongside Japanese vacuum tubes from the same era. The size difference is immediately obvious. The American tube is perhaps 1/3 the volume of comparable Japanese tubes, but the more significant difference is invisible. The American tube was designed to survive being fired from a gun. The Japanese tubes were designed for radio sets and other applications where the harshest environment they would face was being dropped on the floor. That difference, multiplied across thousands of components and dozens of technologies, explained why one nation had proximity fuses and the other did not. Modern visitors to the museum, most of whom have no technical background, often pass the display without much interest. It is just a vacuum tube, an obsolete technology from a distant war. But engineers who understand what they are looking at sometimes stand before that display case for long periods, contemplating what that small glass tube represents. It represents the moment when Japanese engineers had to confront the fact that their fundamental assumptions about what was possible were wrong. It represents the collision between theoretical analysis that concluded something could not be done and physical evidence that it had been done. And it represents the psychological shock of realizing that the enemy you had been fighting was not just larger and wealthier, but was operating with technical capabilities that exceeded your understanding of what was achievable. The proximity fuse never killed Tanaka or any of his colleagues. They survived the war and went on to contribute to Japan's reconstruction. But in a metaphorical sense, the proximity fuse killed something important. It killed the illusion that Japanese technical sophistication could compensate for American material superiority. It killed the belief that American industrial production was just quantitative rather than qualitative. It killed the assumption that the war could be won through superior spirit and tactical innovation, despite material disadvantages. Those illusions had already been dying by 1945, killed by defeat after defeat, by the destruction of the fleet, by the firebombing of cities, by starvation and fuel shortages, and the grinding reality of a losing war. But the proximity fuse delivered a particular kind of death, the death that comes from irrefutable evidence that contradicts everything you believed was true. When Tanaka tested those American vacuum tubes and watched them function after being fired from a gun, he was witnessing the collapse of an entire framework of assumptions. Japanese engineers had carefully analyzed the proximity fuse problem, identified real technical obstacles, and concluded those obstacles were insurmountable. That conclusion had been reasonable, logical, and completely wrong. Americans had surmounted the obstacles by refusing to accept them as insurmountable. This was a lesson about technical problem-solving, but it was also a lesson about strategic thinking and national character. Wars are not won just by having more resources. They are won by using those resources effectively, by investing in innovation, by accepting that today's impossible problems might be tomorrow's solved challenges if enough effort is applied. The proximity fuse demonstrated that American society had internalized these lessons in ways that Japanese society had not. The technical specifications of the proximity fuse are well documented now. The Mark 32 fuse used in 5-inch naval guns contained 4 miniature vacuum tubes, 22 capacitors, 18 resistors, 5 inductors, and associated circuitry. It weighed 2.3 pounds, operated at 180 to 220 MHz, and cost approximately $18 in 1945, after production techniques had reduced costs from over $700 per unit in early 1942. American industry produced over 22 million proximity fuses during the war, representing an investment exceeding $1 billion 1940s dollars. The fuses were credited with dramatically improving anti-aircraft effectiveness, particularly against kamikaze attacks in the final year of the war. But statistics and technical specifications do not capture the human dimension of the story. They do not capture what it felt like for Japanese engineers to hold an American proximity fuse and realize they were examining technology their own nation could not replicate. They do not capture the psychological impact of understanding that the war had been lost not just on battlefields, but in factories, laboratories, and design studios where American engineers had solved problems that Japanese engineers had declared impossible. The proximity fuse was not the reason Japan lost World War II. Japan lost because it attacked nations with vastly greater industrial capacity, fought a multi-front war it could not sustain, and made strategic decisions that proved catastrophically wrong. But the proximity fuse was a perfect symbol of why Japan lost. It represented everything about American industrial power that Japanese strategic planning had failed to account for: the ability to solve impossible problems, the willingness to invest vast resources in technical development, the industrial infrastructure to mass-produce sophisticated devices, and the confidence to use expensive equipment as expendable munitions. For Tanaka and the other engineers who analyzed American proximity fuses during those final months of the war, the knowledge was both illuminating and crushing. Illuminating because they gained insight into advanced technologies and manufacturing processes that would prove valuable during post-war reconstruction. Crushing because they understood, with absolute clarity, that they had been fighting an enemy whose capabilities they had fundamentally misjudged. Years later, during the 1960s, Tanaka gave a lecture at Tokyo University about wartime technical intelligence. He described the experience of testing those American vacuum tubes, watching them function after being fired from a gun, understanding what that meant. A student asked if Tanaka had felt despair at that moment. Tanaka thought carefully before answering. "Not despair," he said. "Recognition. We had been fighting based on assumptions about what was possible. In that moment, I recognized our assumptions were wrong. The war was already lost by then. This just made it clear why. That recognition, painful as it was, proved valuable. Post-war Japanese industry did not try to replicate American methods exactly. Instead, Japanese engineers studied American approaches to quality control, miniaturization, and systematic problem-solving, then adapted those approaches to Japanese circumstances. The proximity fuse became a case study in how American industry approached technical challenges, not by accepting limitations, but by investing resources to overcome them. The vacuum tube technology that had seemed impossible to Japanese engineers in 1942 became routine in American production by 1943. This was not because American engineers were inherently more capable, but because American industry could afford to fail repeatedly during development, could invest in specialized equipment and training, and could maintain parallel development programs, exploring multiple solutions simultaneously. Japan's industrial base, strained by the demands of fighting across the Pacific, could not support that kind of exploratory development. Every resource had to produce immediate results. Long-term research programs with uncertain outcomes were luxuries Japan could not afford. This created a vicious cycle, where Japanese technology fell progressively further behind because resources were always needed for immediate production rather than future development. The proximity fuse illustrated this dynamic perfectly. Japanese engineers had correctly identified the technical problems. They had even conceived of potential solutions similar to what Americans eventually implemented, but they lacked the resources to pursue those solutions through the years of development required to make them work. American engineers started proximity fuse development in 1940 and had working prototypes by mid-1942. But those first prototypes worked only 50% of the time. In any resource-constrained environment, a 50% success rate would have killed the program. The tubes that failed during firing represented wasted resources. The time spent testing and redesigning was time not spent on proven technologies. But America's industrial capacity was large enough to absorb those failures and continue development. By early 1943, reliability had climbed above 90%. By late 1943, proximity fuses were being manufactured by the tens of thousands daily. The willingness to accept initial failures and continue development until the technology matured was something Japan could not afford. Japanese prisoners of war held in American camps during 1945 and 1946 often remarked on the casual abundance they witnessed. Food that would have been luxuries in Japan was routine in prisoner camps. Equipment that would have been carefully maintained and repaired in Japanese service was discarded and replaced in American service. This abundance extended to military technology. Americans used proximity fuses, knowing that most would be destroyed without ever engaging a target. They fired them over water where duds would sink and be lost. They expended them during training exercises. This casual expenditure of sophisticated technology demonstrated a productive capacity that Japanese prisoners found difficult to comprehend. One former naval officer, interviewed in 1946, described watching American ships fire anti-aircraft barrages during an air raid on the camp near San Diego. Every shell appeared to explode in mid-air with perfect precision. The officer, who had studied proximity fuse technical intelligence before his capture, understood what he was watching. Those were proximity fuses being fired in training, he said. Each one cost more than a month's pay for a Japanese sailor. And they were firing them just for practice. That is what we were fighting. The post-war period saw rapid advancement in electronics technology, much of it building on techniques developed for proximity fuses. Miniaturization methods, quality control processes, and circuit design approaches pioneered during wartime production were applied to peacetime applications. The transistor, invented at Bell Labs in 1947, would eventually make vacuum tubes obsolete. But the techniques developed to make rugged vacuum tubes for proximity fuses translated directly to making rugged transistors for military applications. The integrated circuit, developed in the late 1950s, used printed circuit techniques that had been pioneered for proximity fuses. The entire revolution in electronics that defined the second half of the 20th century was built partly on foundations laid during proximity fuse development. Japanese engineers, rebuilding their nation's electronics industry during the 1950s and 1960s, studied American manufacturing techniques carefully. They learned about statistical process control, about continuous improvement methodologies, about systematic approaches to quality management. Many of these techniques had been developed or refined during wartime production, including proximity fuse manufacturing. The irony was that Japan's post-war electronics industry eventually surpassed American consumer electronics manufacturing in many areas, using lessons learned partly from studying American wartime production methods. But that success came decades later, after Reconstruction, after fundamental reforms in how Japanese industry approached manufacturing and quality control. During the war itself, the gap had been insurmountable. Commander Tanaka retired from government service in 1962 and worked as a consultant for several electronics companies during the 1960s and 70s. He rarely spoke publicly about his wartime work, but he maintained detailed personal journals that were donated to the National Diet Library after his death in 1987. Those journals reveal a man who spent decades thinking about the proximity fuse and what it represented. In an entry from 1973, Tanaka reflected on the cultural dimensions of the technical gap. Americans, he wrote, approached engineering problems with an assumption that solutions existed and could be found through sufficient effort. Japanese engineers approached problems with an assumption that solutions must work within existing constraints. Both approaches have value, but in wartime, the American approach proved superior because it allowed breakthrough innovations that changed the constraints themselves. Tanaka described a conversation he had with an American engineer in 1956 during a technical exchange program. The American had worked on proximity fuse development at the Applied Physics Laboratory during the war. Tanaka asked him how American engineers had solved the problem of making vacuum tubes survive artillery acceleration. The American's response was illuminating. "We didn't solve that problem," he said. "We solved dozens of smaller problems, better glass formulations, stronger filament designs, improved mounting techniques, better potting compounds. Each small improvement contributed to the overall solution. We just kept working on it until we got there." This methodical, persistent approach to technical problems was something Tanaka came to see as characteristically American. Not brilliant flashes of insight, though those occurred, but systematic application of resources to solving problems through incremental improvements. It was an approach that required confidence in eventual success, willingness to accept temporary failures, and, most critically, resources sufficient to support years of development. Japan in 1940 through 1945 had lacked all three. Confidence was undermined by resource shortages and military setbacks. Temporary failures could not be afforded when resources were desperately scarce, and the resource base was inadequate even for maintaining existing production, let alone funding speculative development programs. The proximity fuse story thus became, for Tanaka and others who had studied it during the war, a parable about the relationship between technical capability and national resources. Technical problems that seemed impossible under resource constraints became solvable when constraints were removed or lessened. And national resources were not just about raw materials or factory capacity. They included educational infrastructure that produced trained engineers, research institutions that explored fundamental science, industrial organization that supported systematic development, and economic systems that could allocate vast resources to long-term projects. America in 1945 possessed all of these. Japan possessed some of them, but not in sufficient depth or breadth to compete when the competition involved massive industrial production of sophisticated technologies. This was the lesson encoded in that small glass vacuum tube sitting in its display case. Technical achievement was not just about clever engineering or scientific brilliance. It was about the comprehensive infrastructure, resources, and organizational capabilities that turned scientific concepts into mass-produced weapons. The psychological impact of this realization extended beyond the engineers who directly studied proximity fuses. As knowledge of American technical achievements spread through Japanese military and scientific communities during the final months of the war, it contributed to a broader reassessment of what Japan was facing. The kamikaze tactics employed from October 1944 onward were born partly from desperation. Conventional approaches were failing. Pilot training had deteriorated as experienced. Aviators were killed and replacement training was rushed. Fuel shortages limited training flight time. Aircraft quality declined as manufacturing resources were strained. In this context, Suicide tactics that required minimal training and accepted aircraft losses seemed like rational adaptations to resource constraints. But proximity fuses made even suicide tactics progressively less effective. Kamikaze pilots needed to reach their targets. Proximity-fused anti-aircraft fire destroyed aircraft before they could complete their runs. By spring 1945, kamikaze effectiveness had declined to the point where the tactic was consuming aircraft and pilots faster than it was sinking ships. Intelligence officers analyzing kamikaze results could see the declining effectiveness in the statistics, though they did not always connect it specifically to proximity fuses. But after proximity, fuse capabilities became known through technical intelligence in early 1945, the term correlation became obvious. American ships had become significantly more dangerous to attack precisely when proximity fuses entered widespread use. This fed into broader strategic reassessments happening within Japanese military leadership during the final months of the war. If conventional tactics could not succeed, and suicide tactics were becoming ineffective, what options remained? The official answer was to continue fighting, inflict maximum casualties on American forces, and hope that American public opinion would eventually force a negotiated settlement rather than demanding unconditional surrender. But officers studying intelligence reports about American capabilities increasingly doubted this strategy would succeed. Americans who could develop proximity fuses, who could manufacture them by the millions, who could deploy them casually as expendable munitions, did not seem likely to be deterred by casualties. The proximity fuse demonstrated not just technical capability, but willingness to invest massive resources in weapons development. That same willingness would presumably extend to accepting casualties necessary to achieve total victory. This assessment proved accurate. American forces continued advancing despite heavy casualties at Iwo Jima and Okinawa. American bombers continued firebombing Japanese cities despite losses to anti-aircraft fire and fighters. And ultimately, American leadership used atomic weapons to force surrender rather than accepting a negotiated peace that might leave Japanese military power intact. The proximity fuse was not responsible for these strategic decisions, but it was a signpost pointing toward the reality that Japanese strategic planning had consistently misjudged American resolve and capability. Every assumption about American character, American willingness to accept casualties, American industrial limitations, had proven wrong. The proximity fuse was just one more piece of evidence in a comprehensive pattern. By August 1945, when atomic bombs destroyed Hiroshima and Nagasaki, the engineers who had studied proximity fuses were not surprised that Americans had developed atomic weapons. They were surprised only by how quickly Americans had weaponized nuclear physics. The Manhattan Project, like the proximity fuse program, represented massive resource investment in technically challenging development. Both succeeded because America could afford to fail repeatedly during development and could maintain large-scale programs through years of work before achieving practical results. Japan had known that nuclear fission was possible. Japanese physicists had conducted research on nuclear physics before and during the war. But Japanese leadership had concluded that weaponizing nuclear fission would require resources far beyond what Japan could allocate and would take years or decades to achieve. That assessment was correct. For Japan, it was wrong about America. The pattern repeated, across multiple technologies. Americans developed long-range heavy bombers that could strike Japan from distant bases. Americans developed sophisticated radar systems that could detect aircraft at extreme ranges. Americans developed fire control computers that could calculate targeting solutions faster and more accurately than human gunners. Americans developed synthetic rubber production when natural rubber supplies were cut off. Each of these represented technical challenges that required massive development efforts and substantial resource investments. Japan had identified the same needs, pursued some of the same research directions, but could not match American development pace or production scale. The cumulative effect was overwhelming. By 1945, American forces possessed technological advantages in multiple domains. Proximity fuses were just one advantage among many, but they were particularly significant because they made American anti-aircraft defenses, artillery fire dramatically more lethal. The lesson for Japanese engineers and military officers was painful but clear. Technical sophistication was necessary, but not sufficient for military success. It had to be backed by industrial capacity, resource availability, and national infrastructure adequate to support large-scale development and production. Japan had sophisticated engineers and scientists, but Japanese industry could not support development programs on the scale America routinely conducted. This understanding shaped post-war Japanese industrial policy. The engineers who had studied American proximity fuses and other captured technologies during the war became advocates for industrial modernization, quality control systems, and research infrastructure during Reconstruction. They had seen firsthand what American industry could accomplish. They wanted Japanese industry to develop similar capabilities, not for military purposes, but for economic competition and national development. The proximity fuse thus had a legacy that extended far beyond its wartime use. It became a symbol of what modern industrial capacity could achieve when directed toward solving difficult technical problems. It became a case study in systematic development, quality manufacturing, and the relationship between technical innovation and national resources. And for the engineers who had examined it during those desperate final months of the war, it remained a reminder of how profoundly they had misjudged what they were facing. The vacuum tube in the museum display case, that small glass component no larger than a thumb, represents $60 million in development costs, spread across 3 years of research. It represents contributions from over 1,000 scientists and engineers. It represents production from over 100 factories employing tens of thousands of workers. It represents a supply chain spanning the entire United States, coordinating deliveries of specialized materials, components, and assemblies. All of that infrastructure, all of those resources, all of that effort to produce a device that would be fired once and then destroyed, whether by successful detonation or by sinking into the ocean as a dud. The wastefulness was intentional. Americans could afford to be wasteful because their productive capacity was so vast that wasting sophisticated equipment was more efficient than trying to conserve it. This casual abundance, this willingness to expend resources freely in pursuit of military objectives, was something Japanese strategic planning had never adequately accounted for. Japanese military doctrine emphasized efficiency, conservation, and making maximum use of limited resources. These were valuable principles for a resource-constrained nation, but they became liabilities when fighting an enemy for whom resources were effectively unlimited. The proximity fuse encapsulated this asymmetry. Japanese engineers could have designed proximity fuses, given enough time and resources. They understood the principles. They had conceived of similar approaches, but they could not afford the development time, could not allocate the resources, and could not build the industrial infrastructure necessary to manufacture the devices at scale. America could afford all of those things, and did. That was the difference that mattered. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.